Hey, good afternoon. So to start out with, let me just say where we are and all that kind of stuff. According to the syllabus, I'm doing Chapter 9 today, and I will do Chapter 9 today. But I have a little bit of kind of loose ends to pick up on, which is change of scale. So change of scale is something that appears in Chapter 5. So a little bit of your homework that's due at the beginning of next week has to do with change of scale. And change of scale also comes up on the handout. So the second page of the handout has a little bit about change of scale. And then change of scale shows up again at the beginning of Chapter 9. So because I've been a little bit behind, and just because it kind of works well this way, I think, I'm going to do all the change of scale stuff now. Okay, so I'll sort of wrap up those loose ends from Chapter 5 in the handout, do the little bit of Chapter 9 that talks about change of scale, and then get into the rest of Chapter 9. Okay? And the handout for Monday, so Monday's lecture is officially on a handout. That handout's on bSpace now. As of this morning, I can't remember when I put it up, late this morning sometime. So if you opted to get emails, you should have gotten an email saying that it is there. If not, it's there. So if you want to look at that before Monday's lecture and maybe bring it to Monday's lecture, that'd be great. And so that's where we're at. I think there's one more thing. I think that won't take all of Monday's lecture, so I think I'll probably actually get to Chapter 10 a little bit on Monday if you feel like starting to read a little bit of Chapter 10 too. Okay, any questions or comments about what's going on? Okay, also a quick reminder, first quiz is due in section also, so you have a homework due and also the quiz due. The third homework is on the second handout. So just like the second homework was on the first handout, yeah, your assignment that's due a week from this coming week is on that handout. Yeah. No, we skipped 6 and 7. She asked what chapters did we skip. We skipped chapters 6 and 7. So we did Chapter 3, histograms. Chapter 4 was about summary statistics, average, median, SD. Chapter 5 is about normal curve. We skipped 6 and 7. And then Chapter 8 I did last time. So Chapter 8 is about correlation. And today I'll do Chapter 9. And then also the handout, obviously. Okay, any other questions? Yeah. So he asked, if I don't cover something like the SD line, does that mean it won't be on exams? So I actually will cover the SD line, but later on. So if you look further along the schedule, section 8.3, which discusses the SD line, I skipped now. I don't feel like it really belongs in Chapter 8, personally. So I'm going to cover it a little bit later, that particular section. So yeah, specifically the SD line I will hold you responsible for once we get to a midterm. The last part of Chapter 3, which I didn't cover, which does some stuff about cross tabulation and controlling for variables, that stuff I won't hold you responsible for. So, and as I said before, before the midterm, I'll give you a study guide that sort of details what parts of what chapters you're responsible for. Okay, any other questions? Okay, so change of scale. So change of scale, in Chapter 5, change of scale is discussed for the average, the median, and the standard deviation. In Chapter 9, change of scale is discussed for correlation. And like I said, I'm going to sort of cover it all at once. So what do I mean by change of scale? Change of scale is anything where we add, subtract, multiply, or divide. Add, subtract, multiply, or divide all values by a constant. I'm sorry, let me if you're writing this down, hold on a second. Okay. All values, and I just want to say parenthetically, of one variable. If I'm talking about average, median, standard deviation, there's only one variable there. But if I'm talking about two variables, I want to say specifically I'm talking about doing one of these operations to all values of one variable. Or divide all values of one variable by a constant. That sentence doesn't quite make sense in English in the sense that you would multiply by a constant, you would divide by a constant, but you would, I guess, add. You wouldn't add by a constant. I don't know if that's correct English, but yeah. So add a value, add some constant value to all the values of one variable, or subtract a constant from all values of one variable, or multiply or divide. Okay, so that's what I'm talking about when we're talking about change of scale. And I'll sort of go through different cases, and basically, if you do one of these things to all values, maybe of one variable, what we're talking about is what happens to these various summary statistics. What happens to the average, what happens to the median, what happens to the SD, and finally what happens to the correlation if we do one of these things. Okay, so that's sort of the big picture of what I'm talking about when I say change of scale. So I'll go through this kind of case by case. The first case is adding or subtracting. So add or subtract. All values. I'm sorry. Let me say it this way to make it add or subtract a constant to or from all values. And again, if I'm talking about correlation, I need to specify that I'm just talking about of one variable. Okay, so add to or subtract from all values. So I'm going to sort of talk through this in terms of a particular case. Mostly, I want to show a little bit, just one thing for using the summation formulas. What happens if I add a constant? So suppose I have a bunch of values, x1 through xn. Up to xn. Now I want to think about what happens if I add a constant to all those, and I'll think first about the average. What happens to the average? So if that's my original list, x1, x2, x3 up to xn, my new list is going to look like this. So x1 plus some constant, right? And then x2 plus that same constant. And x3 plus that same constant. Okay, up to xn plus that constant. Whatever that constant value is, doesn't change. So then the average of the original list I'll just call that x bar, right? My little shorthand notation from the handout. I can write that as the sum I equals 1 to n of those values xi divided by n. So basically, I'm just saying, add them all up, add up all the original values, divide by n. That's the average. And the average of the new list well, the new values, rather than just the xi's themselves, are xi's plus a constant. This is a little bit of just review back to that handout. So if I add up those values, right, these values up down here, if I add up these things, x1 plus the constant, x2 plus the constant, and so forth, my sum looks like this on top. So the first term would be x1 plus the constant. The second term, when I equals 2, would be x2 plus the constant, so forth. So using my little properties from summation, I can first of all separate this into two different sums. This is, I guess, property C that I listed on that handout. So this is sum I equals 1 up to n of xi plus, so that's the first sum of all those first terms, plus I can think about this as I equals 1 to n of the constant, divide by n. So the first part, sum of xi over n, is just the original average. So I'll write that as x bar, the original average of the list, plus this. And this is actually, you might think a little bit about this. This is written explicitly on that handout as the first property. What happens if I add up a constant n times? I think this confuses people a lot. If I add up that constant n times, I get n times that constant, and then I'm going to divide by n, right? So this is n times the constant divided by n. That sum is just c plus c plus c plus c plus c n times. So that's n times the constant divided by n. And finally, I get x bar plus that constant. The n's cancel. OK, so this is a little bit maybe, I don't know, long-winded or something, more work than maybe you need to do. But I kind of wanted to just make it clear that these things, these change of scale things that I'm doing can be proven explicitly from the summation formulas. I won't do it for all of them. I just wanted to sort of show you this and then kind of talk about it intuitively for most of them. So intuitively, what's going on is it's kind of like what would happen if I took the weights of everyone in the class and the average weight of the class, people in the class, I don't know, say it's 150 pounds. So then let's say that we all drink 2 pounds of water, okay, 32 ounces of water. Step on the scale again. So everyone's weight has gone up by 2 pounds. That's the idea here, is that I'm adding a constant amount to everyone. Everyone gains 2 pounds. What happens to the average? The average goes up by 2 pounds. So I think that shouldn't be too surprising, right? So that's the idea here. Whatever the old average was, the new average of the list is going to be just add on that constant, okay? Subtracting a constant does the same thing to the average. It just goes down by that much, okay? If everyone went to the bathroom and left a pound there somehow, then the average would go down by a pound. Okay. Okay. Right. So, sorry? Okay, so I'll discuss percent. And I know you're curious because there's a homework problem like that. Yeah, so let's talk about median and standard deviation and correlation first with adding or subtracting a constant. So again, I wanted to mention so I sort of said intuitively why the average should go up or down when you add or subtract a constant. And what about the median? So the average, like I said, goes up or down by a constant. What about what's going to happen to the median? Anyone? Median, yeah. Yeah, the median is also going to change by that constant, whatever it is. So I'll go through a little quick example. My numbers, 1, 3, 4, 5, 7. So let's see, example. So just drawing a quick picture of these. I don't care so much about the vertical axis or anything. I just want to give you a quick picture of what the histogram would look like. Okay. So 1, 3, 4, 5, 7. Suppose I add 3 to all values. Now my new list, the 1 is going to change into a 4. So I'll just sort of use the same axis here. I guess 7, 8, 9, 10. 4, 5, 6, 7, 8, and 10. So the 1 changes into a 4. 3 changes into a 6. And then 4 goes to 7. 5 goes to 8. And then finally, the 7 turns into a 10. So first of all, the average, you can see it used to balance at 4. This histogram used to balance at 4. If I sort of imagine this is a solid object, solid blocks or something. Now it's going to balance at 7. So the average went up by 3. Median, half the area is on either side of the 4. Here, half the area is on either side of the 7. Okay? So median goes up by 3 also. Same thing. And what's going on here in terms of the picture is that adding a constant or subtracting a constant is basically leaving this kind of structure the same. It's just moving it to the right or to the left. So all the points are kind of the same relative to each other. I'm just shifting everything over to the left or the right when I add or subtract a constant. Okay, so what happens if I, okay, so this median also changes by that constant. Whatever that constant is, the median is going to go up or down by that amount. Okay, so what about the SD? What's going to happen to the SD here if I add a constant? Yeah, so it stays the same. So why does it stay the same? Yeah. Yeah, good. The relationship between the numbers is still the same. And in particular, the deviations from average are still exactly the same. So this 1, the average here in this first list, 1 is 3 less than the average. Here, the average is 7 now. 4 is also 3 less than the average. So the deviation from average for that point didn't change. The 3 is still 1 below. The 6 is 1 below. Or sorry, the 3 is 1 below here. 6 is still 1 below here, and so forth. You know, the deviations from average stay the same. So that's why that stays the same. Okay. And finally, I want to talk about the correlation. So what's going to happen to R? So now I have to clarify, this thing I said here about one variable. So suppose I have a bunch of x values, a bunch of y values. If you want, you can think about the ones that I did last time. First data set was x is 1, 3, 4, 5, 7, and y is those same numbers in a different order. I guess there's 3, 1, 7, 5, 4, I think it was. 3, 1, 7, 5, 4, something like that. Anyway, if you think about just doing something to one of the variables, so let's say we add 3 to all the x values, leave the y's alone, what do you think is going to happen to R? Any thoughts? That's maybe a little bit harder to get your head around. Yeah, so I'm adding, if you want to imagine the data I had last time, or just any data set you have, suppose I add 3 to one of the variables, leave the other one the same, or add any constant to one of the variables, leave the other one the same. What will happen to the correlation between those two variables? Someone said stay the same. Someone said increase or decrease. I couldn't quite hear. Decrease. It's going to stay the same. Now, why is it going to stay the same? So how do you calculate R? Let me just write it first. R stays the same. So if we add a constant to, for example, all the x values, then think about how you calculated R. So to calculate R, the first step is to convert to standard units. Convert x and y to SU. Well, what do I mean by converting to standard units? I take the value, I subtract off the average, I divide by the SD. So if I add 3 to all the x values and then convert to standard units, well, okay, so with the original data, converting to standard units, I'd have 1 minus 4 divided by the SD. Here, if I convert to standard units, I have 4 minus 7 divided by the SD. The SD is the same in both cases. Okay? It's 2 in this example. The SD is 2, but it doesn't matter, right? The point is that since the SD stays the same, and on top, the standard units for x, the first value is going to be 1 minus 4, which is negative 3. Here, the first value on top is going to be 4 minus 7. And then in both cases, I'm dividing by the same SD. I'm not changing the standard units. If I add 3 to all the x values, going from here to here, don't change the standard units. And that's really what is important in terms of the correlation. The first step is to convert those to standard units. So anything I do from then on is going to be exactly the same. Yeah? R is the correlation coefficient. This is correlation coefficient. Okay? Subject of Wednesday's lecture, right? So R is the correlation coefficient. To calculate R, just to remind you, first step is to convert x and y to standard units. Second step is to take the products of the standard units. Third step is take the average of the products. But my point here is just that since the first step is to convert x and y to standard units, if the standard units don't change, then R isn't going to change. So R stays the same. So R unchanged. since SU unchanged. Okay. So in fact, it doesn't matter if I, add a constant to the x's and leave the y's alone, or I could add a constant to the y's also. I could add different constants. I could subtract a constant from a list. Doesn't matter. Anything I do that shifts one of them over left or right, or both of them over left or right, doesn't matter. And yeah, excuse me. So the standard units aren't changed. Another way to say this is the way that this question was answered about the SD, just basically that they don't change kind of relative to each other if you move them over. Okay? If you want to think about this in terms of a picture, if I had like a scatter diagram there, add a constant, what's happening? Well, you might think of it as just same picture, just moved over. So if you think about like, well, how close are the points to a line, it's kind of the same, right? Okay. All right. Questions about that? Okay, so that gets us through adding and subtracting constants. Now let's talk about multiplying and dividing. And this I want to divide into two parts. The first part is to think about multiplying by a positive constant. And I'll just stick in here, or divide by a positive constant. So, I mean, division is basically multiplying by the reciprocal, right? So if I want to think about dividing by 2, I could just as well think about multiplying by a half. So, when I say or divide here, I'm not really going to talk about division because it's just the same as multiplication. Okay, so multiply by a positive constant. Let's think about what happens to the average. So if you want, you could think about doubling all the values, multiply them by 2. What will happen to the average if I do that? It's going to double. What about the median? Also double. Okay, so average and median will double. Or get multiplied by that constant in general. And to see that, I'll go back to this, and I'll think about what happens if I double those. So double 1, 3, 4, 5, 7. I get 2, 6, 8, 10, 14. And the average of those is now going to be 8. The median is also going to be 8. So maybe you can just kind of see that. Let me draw a quick picture like I did over there. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 2, 6, 8, 10, and 14. So now my picture is going to look like this. 2, 6, 8, 10. Oops, these should be centered on those values. And 14. Okay? So I get a picture that looks basically like that. And average is where it balances. It's going to balance in the middle at 8, and then half the area is on either side of 8. So that's a little quick argument, at least, that the average and the median should also double in this case, and in general get multiplied by that constant. Okay? Any questions on that? Okay. So like I said, for I could do a similar proof to that up there, but it's kind of long. I won't bother with it. But yeah, at least I want to give you the intuitive explanation of why this works. Okay, so what about the standard deviation? So what happens to the standard deviation if I double all the values? Thoughts? Yeah. Stays the same? Anyone else? Yeah? It doubles? Gets multiplied by the absolute value, someone said? So right now I'm just talking about multiplying by a positive constant, okay? So absolute value is not relevant yet. But let's think about what the SD measures. So the SD measures kind of the typical distance from the average. Now, in this case, with 1, 3, 4, 5, 7, the numbers, the deviations from average, right? The 1 is 3 away, the 3 is 1 away. Deviation from average would be -3, -1, 0, and then 1, and then the 7 is 3 above, so that deviation is 3. Okay? So that's my deviations from average there. Here, well, this first one is 6 away now, right? Used to be 3 away, now it's 6 away. The 6 came from the 3, so the 3 was 1 away, the 6 is now 2 away, 2 below. 0, 2, and 6. You can see all the deviations from average actually got doubled. So intuitively, I hope at least, it makes sense that the SD is going to be doubled then. And that's what happens, right? So the SD also gets multiplied by the constant. Okay? So average, median, SD all get multiplied by the positive constant. Okay, any questions on those? Okay, so correlation is last. R, correlation. What do you think is going to happen to that? Any thoughts? It's a little bit trickier. R, I think, is in general. Correlation is in general a little bit harder to think about as a descriptive statistic. Anyone? Hand or yeah? Stays the same? Yeah? Correlation gets weaker. So why do you say it gets weaker? Yeah, good. So her intuitive thought about this, and this is a very common intuitive thought. I'm sorry, it turns out to be wrong. But I want to bring it up because I think it's very common to think that, well, if you double all these x values, you change them into 2, 6, 8, 10, 14, somehow things are getting spread out. Seems like that makes like the relationship weaker between x and y. Or you might think that since you're sort of stretching things out, that maybe the picture gets stretched out and maybe the correlation gets stronger. Maybe the points seem to get closer to a line, right? I think those are two very common intuitive thoughts that somehow, by spreading them out, you make things either weaker, or by stretching out the picture, you make the correlation stronger or closer to 1. Both those turn out to be wrong. R stays the same, and you can actually think about this just the same way as we thought about this for adding a constant. So at the end, I said R is unchanged since the standard units are unchanged. Let's think about what happens to the standard units in this case when we multiply by a constant. Standard units look something like, value minus the average divided by the SD. So if we double all the values, we already said the average gets doubled also, right? So if you think about that list 1, 3, 4, 5, 7, what happens to the standard units? Standard units is value minus average divided by SD. Values all get doubled. Average gets doubled. The SD also gets doubled. So since everything on the top and the bottom all gets doubled, the standard units overall are going to be unchanged. So unchanged. So by the same argument as before, so R is unchanged. Okay. Now, I think R is, part of the reason why I'm spending a little bit more time on this one, I think, is that R is a little bit hard to think about intuitively. And I like to sort of think about it as something that describes something about the picture. And you can think of moving the picture over, left to right, or multiplying by a constant as really a relabeling of the axes, okay? If I have some labels on the axis here, like 1, 2, 3, 4, 5, and I multiply everything by 10, well, I could just change the labels on the axis to 10, 20, 30, 40, 50. And in a sense, I haven't really changed the way the picture looks, right? So since it's measuring something about that picture itself, that's a little bit of an intuitive argument about why, doubling or adding a constant or anything like that isn't going to change the correlation, because it's measuring something about the way the data looks, the picture of the data. Okay? So, any other questions about this? Okay, so let me do so there's actually the last two very short last bits I want to do. One is what happens when the constant's negative. so 3 multiply or divide by negative constant. So first to the average and the average and the median multiplied by that constant. And I hope that's fairly intuitive. So let's just think about what happens if I multiply by -1, right? If I multiply by -1, this gets kind of flipped over, right? So 1 is the smallest value here. When you flip it over, actually, it's the biggest value, right? -7 is the smallest. It's the most negative. -1 is the biggest. So the order changes, in a sense, by flipping it over. But the average is, or the balancing point is still going to be -4 if I imagine that histogram flipped over, okay? It's going to be that, whatever happens to that point, it's still going to be the average and the median. Okay, so average and the median get multiplied by that constant. What about the SD? You know. Multiply by the absolute value, right? So yeah. SD gets multiplied by the absolute value. Of the constant. Okay, so if in my little example of multiplying by -1, I'm not going to change the SD. If I flip these over, the spread's going to be the same, right? The deviations from average are going to be kind of the opposite, but I mean, they're all going to change sign, but the RMS of the deviations from average is going to be the same, okay? So if I think about flipping this over, that would be like multiplying by -2, right? If my new data was -2, -6, -8, -10, -14, now my data is going to have an SD of +2, or twice what it was, sorry. Absolute value of -2, or twice what it used to be with the original, okay? So yeah, so the sort of size of the multiplication is what's important. That tells me how much things are spread out. The sign is irrelevant, whether or not it's a positive or negative constant. Yeah, and maybe that goes back to how you calculate the standard deviation. When you calculate the standard deviation, RMS of the deviations from average, very first thing you do to the deviations from average is square them. So the signs aren't going to matter, right? Okay, any questions on that? Okay, so finally, what happens to R if I multiply by a negative constant? Any thoughts? Yeah. Yeah. The correlation gets multiplied by -1. Now, why is that? I think the easiest way to think about that is to think about a picture. So R gets multiplied by -1. So if I started with this, and I multiply all the x values by -1, the picture is going to kind of flip over to here, right? That would sort of turn into this, if 0's here, okay? Kind of flipping over the picture. And now, I mean, it used to be that you had a kind of upward trend. Now you have a downward trend. But the sort of size of the correlation is going to be the same because the points are kind of the same distance away from a line or something like that. They're clustered in the same way around a line. They're just pointed the other way. Okay? Any, yeah? Yeah, so I sort of said that at the beginning. I guess I didn't emphasize that here. So one variable. I don't know what you mean by not stated in the problem. I think any problem you're given should state whether or not you're going to multiply one of the variables or both the variables by a constant. And I'm a little bit sloppy here. I said it at the beginning. If you go back to the beginning of the lecture, I said, okay, I'm just going to do these things to one variable. So I'm sorry I left it out here. But yeah, what I'm talking about is multiplying or dividing one of the variables by a negative constant. Okay? If I do both of them, what happens? I get back to what I started with, right? It's going to kind of flip over from like that to that, and then from that to that. So at the end, it'll be pointed up again, right? That to that, and then from there, if I multiply the y's by -1, I go to this, which is now positive correlation again. Okay? So one very last thing here I want to mention, which is not really change of scale, but it's in the same section. It's what happens to the correlation if I switch x and y. So interchange x and y. What happens to, so that's, that doesn't, that's not something that makes any sense talking about average, median, or standard deviation. This just has to do with correlation. So what do you think that will do to the correlation? Any thoughts? Yeah. It's going to stay the same. And maybe one way to think about that mathematically is to think about here when I talked about correlation to calculate R, first step is to convert x and y to standard units. Second step is to take the products of the standard units. So if I'm taking products of standard units of x times standard units of y, doesn't matter if I do it in the other order. Standard units of y times standard units of x. Still going to be exactly the same calculation. So that's maybe one mathy way to say it. More intuitive way to say it might be just that if you have a picture with, say, height and weight, if you look at it with the axes switched, weight and height and weight, the basic shape of it's going to be the same. The sort of, like how well the points are clustered around a line is going to be the same if I switch those axes. Okay, so one like final thought about this is that you notice that it's pretty hard to change R, right? R kind of has to do with the picture. Adding constants, multiplying by constants won't change R. Switching them won't change R, except this one case where if I multiply one of the variables by a negative number, that's the one time that I'll get R to switch. Okay, questions, thoughts? Okay, so that kind of took longer than I thought it would. So I'm going to get into Chapter 9, the rest of Chapter 9, but I don't think I'll quite finish everything I want to say about Chapter 9 today. So I'll finish it up on Monday and then do the handout, which, like I said, handout is available on BSpace. So the rest of Chapter 9 sort of has to do with some kind of, I don't know, kind of weird special cases and things like that. So the first couple things, now this is sort of, I just want to connect this back to Chapter 3 and I guess Chapter 5. Chapter 3 talked about histograms, right? Pictures for data. Chapter 5 talked about one particular kind of picture for data, which is the normal curve. It's possible that your histogram might look like the normal curve, and we might think of that as sort of being nice, right? It's sort of nice when the histogram looks like the normal curve. We can use the normal table. We can do all these like little calculations. Analogous to that is the idea of what the book calls a football-shaped scatter diagram. So this is kind of going back to scatter diagrams. And football shape is kind of a non-technical term. A little bit later, especially as we get to Chapter 11. So right now we're in Chapter 9. In a little while, I'll tell you specifically, technically, what I mean by a football-shaped scatter diagram. But for now, just think of football-shaped as being nice. Okay? In the same way that normal curve is sort of nice. When you have something that looks like the normal curve, you get to do some stuff. Wait, I haven't done the stuff yet. The stuff comes in Chapter 10. That's where I start doing the nice things you can do with a football-shaped scatter diagram. And it looks kind of like a football, right? So it might look like that. Or it might be a little fatter or thinner, right? So maybe it's like a stronger correlation like that. Maybe that's kind of a deflated football, or maybe an overinflated football. That's sort of the same as the first one. Okay. So it might actually have correlation pretty close to 0, but the idea is that it sort of has that general shape. Linear relationship and Yeah, sort of nice, okay? That's sort of the typical case that we're kind of hoping for. But there are exceptions. Just like with the histogram looking like the normal curve, there are things like income, housing prices I also talked about a little bit, that don't look like the normal curve. They're like, have these long right tails. Sometimes you have long left tails, things like that. In the world of scatter diagrams, the things that are sort of weird that can go wrong mostly classify in one of these categories. So one of them is nonlinear. So these sort of all, they all sort of so for higher values of x, you sort of have higher values of y. And, you could just as well have a football that way too, right? But whatever, whichever way it's pointed, it has this general linear trend. So nonlinear, as a picture with that, kind of outline in mind, might have something like this, where you have this kind of strange relationship that, goes up and down, and something weird is going on there, okay? You might also have the other way, sort of like this, okay? Or if you want to draw dots, you might, and I think I drew a picture a little bit like this last time, where you might imagine that it's maybe part of a parabola or something like that, okay? So you get some relationship there, but it doesn't follow a line. So you can tell that there's a very strong relationship there, but it's not captured very well by a line. So maybe a real-world example, this might be something like, I don't know. It's a little bit hard to find natural examples of this, but maybe car prices might follow something like that for a certain group of cars where they decline in value, but then like really old antique cars maybe are more expensive or something like that. So, there are sort of a few like real-world examples where something like that might happen. And I'll just mention that R is not a particularly useful summary statistic in these cases. So R is not as useful in these cases. And in the same sort of way that if you have a histogram that has a very long right tail or something like income or whatever, the average and the standard deviation are not quite as useful summary statistics. You can't do all the normal curve stuff. It's, the average and the SD maybe aren't great summaries. So I'll give you a little quick example in class where I had a data set of hypothetical incomes, and I imagined that the CEO or the president of the company gave himself a big raise, earned $1 million, and it made the average kind of not what you would think of as the center of the data. It was sort of like off by itself where no one really had that salary, but it was kind of stretched to the right because of the one very large salary. So in that case, the average was not a particularly great summary statistic to report as like a center of the data. Same sort of way, R is going to be positive here because there's sort of a general upward trend. R is going to be negative here, R is going to be positive here, but it doesn't capture the fact that there's some pattern in the data which is not linear, right? R tells you how well the points follow a line, and especially maybe in this case, well, you might be able to say that there's some line that kind of goes through them, but really there's a very strong relationship that doesn't follow a line, okay? So really you'd like to sort of describe that somehow. Okay, so there's my nonlinear little examples. Any questions about that? Okay, so then another case that's a little bit weird, I think someone asked about this also, is with outliers. So outliers, you might have a scatter diagram that mostly looks like a football, but maybe you have a point up there that sort of is separate, okay? So most of the data is described well by our usual summary statistics. Got this nice football down here, and there's something up there that kind of doesn't follow the same pattern for some reason. So in real life, when you see data that looks like this, I think the natural thing to do is to sort of think about that point and what's going on there. Now, it might be that that point is important that there's like some important reason why most of the data is here, but every once in a while there's something weird that happens and you get a point up there. Or it might be that that's something that we don't really care so much about. And really what we want to do is analyze this. Maybe if we were writing a report or something, we would mention that there's this one value up here, but most of the data follows this pattern. Okay, so we might want to not ignore it, but analyze the rest of the data separately and then mention the kind of exception, right? So it's maybe a typical way of dealing with that is to just think about that guy separately. So you might have something like that. You might actually have something that everything follows a line, except for some reason there's a point up here. Okay? So again, very strong pattern or linear relationship here, but for some reason there's this outlier off in the distance. Okay? So those two things are outliers. Okay? Questions on any of that? Okay, so I want to talk last about what's called ecological correlation. And if I can just set this up real quick. Okay. Okay. So ecological correlation. Doesn't have anything to do with ecology or anything. It's the specific thing. It measures correlation between averages of groups, or maybe I should say subgroups. All right. So I'll give you an example of this. So this is it's warming up. It'll be a second. Oopsie. Okay, so that'll be up there in a second. So what this is doing basically is that the x values and the y values, rather than being values for individuals, like individual students in the class, we have subgroups, and each subgroup represents 1 point. So what this is ecological or aggregate correlation for GPA and income by zip code. So each zip code that has students going to Berkeley High School is 1 point here. So this might be 94702 or something. It's one zip code. And along the x-axis here, we have median income for that zip code. Along the y-axis, we have average. I'm sorry, this is averages or medians. Okay. So along here is the median income. Here is the average GPA, and the correlation is quite strong. 0.87 is you don't have a lot of experience with correlation, but 0.87 is quite strong in the world of like doing social science, okay? So what we're getting from this is that there's a strong relationship between income and the GPA of the students by zip code. So I'll have to talk about this more on Monday, I think. But just very briefly, I'll just say my lesson here is that this often overstates relationships, okay? And I'll talk about why on Monday. I'll show you this picture again. But you can think about this maybe a little bit over the weekend about why that might be, what's going on there, what you think about that picture. Okay? Any questions before I let you go? Okay, so I'll finish that up and finish chapter 9 on Monday.